All right, stats, welcome to your Monday, October 25th video, and we are just gonna get started on chapter 12 here. Chapter 12, I sent you quite a large note packet there. If you wanna print that off at school, that is fine. If not, just really, you can have it up on your Chromebook as well and just take notes on a sheet of paper. This is solely for your notes. I don't check it like a game plan or anything in college algebra. So whatever you want to do, that is fine. Okay, homework sets I send you, do try to print those out for me, please. You have a homework set, which is chapter 10. It's a short one, and I either gave you some big hints or they're essentially what it was in that quiz review that I went all the way through on. So you're going to send that to me like you did your last homework set. Just email that to me. You guys did a good job on that. All right. Anyway, so here is the packet. From time to time, we would look directly at this right here. All right, chapter 12, general rules of probability. And so here's what we know. For any events, A, the probability that anything, that A happens is between 0 and 1. Probabilities are always between 0 and 1. If S is the sample space and the probability of the entire sample space, i.e. it must add to 1, okay? So everything in the sample space, probabilities, they must sum to 1. All right, so we also know this. If A and B are disjoint, that means they can't happen at the same time. Like winning or losing, you do one or the other, okay? You pick one color or the other. You either flip a heads or a tails. Those are disjoint. So then you have the complement. For any event A, the probability that A does not occur is 1 minus the probability of A. We already know that. That is the complements. All right, we have independence and the multiplication rule. So that's what it means if two things are disjoint, there's no intersection. They both cannot happen. All right. So then we have a Venn diagram. We're going to make more Venn diagrams. And notice how you've got a rectangle around this Venn diagram. You guys might have just done that kind of comparing and contrasting where they overlap. There, you didn't have a rectangle. The outside of the rectangle is everything that can't happen in A or B, and it's not going to be 0. All right, so you got A all by just A, just B, and the intersection of A and B, and this is everything that isn't A or B on the outside, and S is the sample space. Okay, then we get to this page 3 right here. So this is an interesting combination of notes, and then obviously past reviews. That's not been edited well. When I'm probably using Word, then I try to get it onto Google Docs, and it does not format well. So let's just get into it. I think none of this is too tough, I don't think, so we can just learn here about it. So a pair of fair dice are rolled. What is the probability that the sum of the dice is 7 or 8, given that the sum is more than 4? So in chapter 10, we made the sample space for the sum. It's this. There's 36 different sums, but I am telling you, number one, X is a sum. I want to know what's the probability of getting a 7 or 8 with the knowledge of that my sum, it has to be more than 4. So I can't have all 36 sums in play. So this is a probability of A given that B must occur. The B in this would be the sum that is 4, that's more than 4. So given that B is going to happen, what's the probability that A happens as well? So that's what the straight line downs, it means given. If you're in calculus, when we have set notation, it means such that. You can kind of think of it like that. What's the probability of A such that B happens? What's the probability of A given B? That's what that means. Please write that down. We'll write a more formal definition and formula for that later. So here's how I would write it, and I do want you to write this for any homework sets, quizzes, and exams. If X is a sum, I want to know the probability that X is 7 or 8, given X is greater than 4. Well, first off, X must be greater than 4. So it can't be 4, it can't be 3, and it can't be 2. So it can only be 30. There's only 30 different sums that are more than 4. So what's the probability that it's 7 or 8? Those 6 plus those 5, that's 11 out of 30, not 11 out of 36. Very important we know that. All right. So that is a good question, and we have run out of room. We are going to go to number 2 here with smoking and degrees. So again, we're going to write a more formal conditional probability formula in later in the chapter. So we're going to be on page 2. They are numbered at the bottom, though. Your first page doesn't have a number, so it's page 0. All right, and it says the following. You can read it there. In a group of 1,000 people, the numbers who do or do not smoke and who do or do not have a college degree are given in the table, are given below. And I've kind of reproduced that. So given that a person is a smoker, what's the probability they don't have a college degree? So the given part always goes second. So you're kind of, some cases and anytime you say given, well, that's not true because C is not that. So a lot of times when you see given, it's going to be a conditional probability. Okay, so what's the condition? You have to pick a smoker. That always comes second. That's the B part, even though it's written first. So what's the probability someone has they don't have a college degree given that they're a smoker? That's what this is saying. So you're going to write your probability statement like that. Given that they have no degree, what's the probability that they're a smoker? So the denominator is going to be all the people that smoke, which is 192 people that smoke. And then what is going to be the numerator? The numerator is going to be no college degree, which is 145. All right, so you're just going to type 145 divided by 192. That goes in the calculator. That is 755. All right. So next part here, given that a person is not a smoker, what is the probability that they have a college degree? So let's take a look. Again, the given part goes second, not a smoker. So you're really asking what's the probability they have a college degree given not a smoker? So what's going to be your denominator? Everyone that does not smoke. That is 808 of them. Find that denominator. So I want the intersection. That's going to be a part of my formula later. The intersection of not smoking and college degree. That's 304 out of 808. It is 376.376. Again, we always round probabilities to 3 decimals. All right, take a look at C. Now, given a randomly chosen person from the sample, so that's, even though it says given, that's not a conditional probability. So that's just anyone at random. What's the probability they don't have a college degree? So there are 1,000 people. So this is just asking what's the probability you pick someone with no college degree. So no college degree, that row is 649.649. All right, the next one is given that a person does not have a college degree. So that's the second part. What's the probability that they don't smoke? So it's what's the probability that they don't smoke given no degree. So my denominator is always this B part, this given. This has to happen. How many people with no degree? That's 649. And of the 649, how many don't smoke? Of the people with no college degree, that row, how many don't smoke? 504. 504 over 649. Triple sevens, right? Let's make sure that no smoke, no degree. Yep. Okay, cool. Given that a person has a college degree, what's the probability that they smoke? So what's the probability that they smoke given that they have a college degree? Right, all your probability statements like that. All right. So probability that they smoke given degree. So first off, we're looking at college degree. There are 341 of them that have a degree, and there's 47 of the 341, or 51. That smoke. 47 of 351. 47 divided by 351, 134. Cool. That is page 2. All right. That is a good page, good question. You'll see that one a bunch the rest of the semester. All right, so what else do I have here? I have us looking at page 4, followed by page 5 of the packet. All right, so we are not going to do that yet. We will the next day take a look at 8 and 9. Those are pretty easy questions. Let's look here. Multiplication rule. All right, just keep multiplying. Look at 12. 3, goodness. So during the Second World War, the British found that the probability a bomber is lost through enemy action is like 5%. That's not good. That seems high. The probability that the bomber returns safely is 0.95. It's reasonable to assume that missions are independent. Take A sub I, the event that a bomber survives the ith mission. So the probability of surviving 2 straight missions, you got a 90% chance. But let's say you're going to have 20 missions total. Holy cow, look at that. The tour of duty for an airman was 30 missions. Oh my goodness. So if you take 0.95, if you raise it to the 30th power, what's the probability that, given a survival rate on each mission of 95%, what's the probability that you make it through? 21.5% chance, less than a quarter of airmen would make it through a tour of duty. Ho, 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 ho. Man. All right. This is a pretty interesting question here with the HIV testing. So you have a false positive rate of 0.004. 0.004. So if a clinic tests 200 people who are actually free of the HIV antibodies, they are HIV negative, what is the probability at least one false positive is going to happen? So again, the probability of at least one false positive is just 1 minus the probability of no false positives here. So the probability that no false positives occur means that you, the chance of, again, if the probability of a false positive is 0.004, the probability of not getting a false positive is 0.996. You want that to happen 200 times. So the chance that you don't have a false positive is that. So that means the chance that you do have at least one false positive is 0.55. There's a 55% chance, or a greater than 1/2 chance that at least one of the 200 people will get the call that they have tested positive even though they don't have it. That would be a bad day. All right, so there you go, 12-1. Government data show that 8% of adults are full-time college students and 30% of adults are also 55 or older. Nonetheless, we can't conclude that 2.4% of adults are college students 55 or older, okay? It would have to be this. It would have to be 8% of adults are full-time students, and of, Yogi, we've talked about this, buddy, and of those full-time students, 30% are 55 or older. That's how we would get, how we can multiply it. That's how we can multiply it. Knock it off. Knock it off. You're going in there. All right, and we're back. Common names. The Census Bureau says that the 10 most common names in the United States are in order: Smith, Johnson, Williams, Brown, Jones, Miller, Davis, Garcia, Rodriguez, and Wilson. All right. These names account for 9.6% of all U.S. residents. 9.6. So those names in total, 9.6% of all U.S. residents. Out of curiosity, you look at the textbooks of your current courses. There were 9 authors in all. Would you be surprised if none of the names of these authors were among the 10 most common? Assume that they are independent. So here's what we're going to do on this one. We're going to do this one together. It's a fun one. So let's let's see, we don't define X here. So the probability of getting an author with one of those 10 most common last names, 9.6%, is that as a decimal? And you want to know, would you be surprised if none of them? So the probability that you don't pick up a textbook and the last name of the primary author, let's say it's just a single author, like calculus and stats, both of your books have a single author. All right. So it's 0.904. We need to, oh no, not to the 10th, but to the 1. You have 9 textbooks to the 9th. All right, 0.904, raise it to the 9th power. 0.403. So there's a 40.3% chance that of 9 randomly chosen books, none of them have an author with one of those last names. So you wouldn't be shocked, but there's a better than likely, there's more likely chance that you're going to pick up in those 9 books, an author with one of those 10 last names. All right, now it says look at page 6, which is the next page. Goodness, Yogi. All right, there's going to be a large dog barking in another room. So disregard that. Yogi is fine. Look at page 6 of the packet. Always fun trying to make videos with a large dog who will not let anything pass outside quietly. All right, so take a look here. Page 6. Addition rule for any 2 events. The probability of A or B is equal to the probability of A plus the probability of B minus the probability that they both happen. All right, that's one way to write it. Here's another way. I like using U. U is for union. Okay, so that's the probability of A, U, B. A or B. U is for union. Union means or. A or B is happening. Plus the probability of A plus the probability of B minus, instead of saying and, we're going to use the upside down U, which stands for intersection. Okay? So probability of A union B is equal to the probability of A plus the probability of B minus the intersection. So you're going to have to memorize. You're going to have to. So this is not a formula that like SIU or SLU or SIUE gives. All right. So it's probably, that's just kind of like a common knowledge formula. Same thing with the conditional probability that we'll talk about tomorrow, I believe. So you're just going to have to know that one. All right, so then we are looking at page 7. What are we looking at on page 7? So on page 7, we're not really utilizing that. We're looking at 12.4 just because this is an interesting question. Of the college degrees awarded in the United States, 50% are bachelor's. So that means if you have 100 degrees, 50 are bachelor's degrees, and then 50 are non-bachelor's, whether it's associates, PhDs, masters, you got it. 59% of all degrees, I believe that's how it's meant right there, 59% of all degrees are earned by women, and 29% of all degrees are bachelor's degrees earned by women. All right, so I don't know why this didn't make a Venn diagram here. Here's how we're going to do it. So this is on another page, as I said. And here is the other page. So let's do that. This is 12.4. This is question 12.4. All right, so I just thought it was a cool question. So here you go. You got college degrees. BA, BS, Bachelor's of Arts, Bachelor's of Science, Bachelor's degree. You got 50 of them. For every 100, 50 are bachelor's degrees and 50 are not. I should say non. All right. Of the 50 bachelor's degrees, 29 of them are earned by women. 21 of them would be earned by men. Now, it said 59% of all degrees were earned by women. This is 100 degrees total. So if that's 29, this must be 30, and that must be 20. So part A, 41% of all degrees are earned by men. 21% of all degrees earned are bachelor's degrees earned by men. Here's what we also know. I can say 29 out of 50, which is 58% of bachelor's degrees, are earned by women. And I can say 21 out of 50, 42% of bachelor's degrees are earned by men. Again, pause this when you need to. And I can say 30 out of 50, or 60% of all non-bachelor's degrees are earned by women, and 20 out of 50, or 40% of all non-bachelor's degrees are earned by men. And we kind of saw this. We had a question like this before. Was it in these chapter 6-8 packets? I forget. Or was it in chapter 10? Anyway, it's been a while. So speaking of being a while, folks, we are going to try to finish this up real quick. And I think this was on page 15 of your packets. Page 15 of your packets. We're going to make a Venn diagram here. And you can read what it says. It says you've applied to both Washington University in St. Louis and Stanford University in California. The probability that WashU is going to admit you is 0.63. The probability of getting to Stanford is 0.58. And the probability that both are going to let you in is 3 out of 8, 0.38. Make a Venn diagram and use it to answer the questions. All right, so A is the event that WashU admits you. B is the event that Stanford admits you. So the probability of A is 0.63, the probability of B is 0.58, and the probability of their intersection, it both happens, is 0.38. So if I'm making a Venn diagram, I don't put 0.63, 0.58, 0.38, because the probability of the whole sample space is bigger than 1. Instead, I start in the middle, and that's a 0.38. The probability of the intersection is 0.38. Then what actually goes in this only A part is not 0.63, but 63 minus 38. So you have a quarter chance that it's only WashU that admits you. What goes into this only B parts is 0.58 minus 38. That's 0.20. All right. Now, if you add up those numbers, it does not add to 1. That's because there is hopefully a small chance neither school admits you. So what you put inside the rectangle, but outside of the circles is the A union B complement. A union B complement. All right? Yeah. So it's going to be 1 minus all those other numbers, the sum of all the other numbers. 63, 83, 1 minus 0.83 is 0.17. 17% chance neither school says yes. What is the probability at least one of the schools admits you? Well, you can do it one of two ways. You can do 1 minus probability that none let you in. So you're going to say probability at least one school admits you. All right. Or probability of A union B. It's 0.83. Probability of A union B is the probability of A plus the probability of B minus the intersection. If you do this plus this minus this, you get exactly 0.83. What is the probability that neither school admits you? That is actually A union B, the complement. Or it's probability at least one school admits you minus that. So probability no admittance. You can always write it like that. All right, what is the probability that only WashU admits you? Probability, so you could say A only, or probability WashU U only. And so the Venn diagram is really what shows your work. All right, it's 0.25. What does probability that only stand for admits you? So probability B only. So it's not the probability of B, because in B is also the chance that A admits you. So no, probability of B only or probability of Stanford. I always want to put the D there. Only. It's actually just 0.20. All right. And I got a dog that wants to be freed here, so we're going to end that. Almost 26 minutes. Great notes. That is it for your Monday, October 25th notes, folks. This is Yak Math Videos signing out.